What's on the smartboard is what we were hoping that you would get to last class with that reading guide that we're going to continue in a little bit about how some ionic compounds can change the pH of water. The reason is some of them can react with the water. It's referred to as hydrolysis. Some of them cannot react with the water. So before you move on with the rest of the reading guide, because today is basically finish that reading guide and introduce buffers. And perhaps the good news for you is that with 2 class periods next week and then spring break, I don't want to do anything past buffers prior to spring break, which means we're going to stretch out a little bit of what we're doing these next few class periods. Hopefully that allows you to really understand what's going on here, because this is where students start to feel what in the world is going on. How in the world is NaF put in water now all of a sudden a basic solution, but ammonium chloride is acidic? Okay, I at least know sodium chloride in water is neutral because I've never been taught anything other than that. So the hope is by spending these next 3 class periods on wrapping up individual ions' effect on pH and then talking about buffers and then taking that into next week where we have a lab, that by stretching this out we have really covered it well. All this breaks down into is based upon, again, interactions with water. But what the reading guide should have taught you last class is that strength plays a role. That even though you do not see a formula of an acid or a base on the board right now, you should be thinking about an acid or a base when we're giving you scenarios like this. So what I mean by that is in NaF, there is the fluoride anion, which is also in hydrogen fluoride or hydrofluoric acid. This is a weak acid. What the double arrow represents is that the reactants can form products, but the products can reform reactants. The products can do something. If I go back to this previous slide, NaCl, however, its root acid would be hydrochloric acid. Hydrochloric acid is a strong acid. Notice I did not use a double arrow for hydrochloric acid because it completely makes its ions. Not only does it completely make its ions, but these things are not going in the opposite direction. And to me, that's key to this, is that understanding of a weak versus a strong. A weak, the products can still do stuff. Sorry, there's a plus sign there. A strong, the products are just done. And what I mean by that is if we now have things dissolved in water. For example, in sodium fluoride, I have the fluoride ion dissolved in water. Since fluoride is the conjugate of a weak acid, the reverse can happen, meaning that this can react with water to reform that. And if it takes a hydrogen from water, it now made hydroxide, making it basic. Because the hydroxide in solution is what makes it basic. HCl cannot do that. Chlorine does not have the option of the reverse reaction when you look at this. So chloride ion is not going to react with the water to make the hydroxide. The other example I give on here is ammonium chloride. Well, I already know the Cl isn't going to do anything in water, but the ammonium can. Because ammonium is the conjugate acid of the weak base ammonium hydroxide. Once it's a conjugate of something weak, that means its products can still do stuff. They are not just done. When you are a product of something strong, or in Chem 1, when most of the reactions we did were single arrow, that means once you hit products, it's over. It's done. That stuff isn't doing anything. But that double arrow changes everything. It now allows more things to happen. So when I have ammonium chloride, like in this last example here, the ammonium part can now interact with water. And in doing so, it can gain that hydroxide back. But now it leaves the acid ion in return, making that slightly acidic. So what you have to do today is first we have to wrap up that reading guide, which some of you got done with the first page, some of you continued on the back page. What you probably didn't get to was question number 4. Question number 4 is going to introduce a new calculation to you that I need you to be aware of. But when we get done with that, again, once most of us are about done, we'll move on with buffers for the day. And again, there's only 2 sheets that you picked up dealing with buffers, although I think the reading guide might take a bit of time because there's a fair amount of math on that as well. But that's also why I gave you another just review sheet in case you are kind of quick with a lot of this and then you have extra time. So I just wanted to start class. I want to wrap up with, for this topic, before we move into what buffers are, is one more little thing to help you out with the math. So the nice thing about the reading guide that we just did is it gave you this equation. Which, remember, that's Kw. That is on your equation sheet. So that equation you don't have to memorize. You just need to know when to use it. And hopefully you just saw today, when do I use this equation? Well, if I'm given an ionic compound and asked what's the pH of it, I can use this if I know the Ka of the acid. Now I can solve for the Kb of its conjugate base and do what I've normally done. It's one extra step beyond what you've done before. And the good news is I don't know of another step after that. So when we say, okay, well, here's just pH equals negative log. Hey, you guys learned that. Oh, no, now we got to add to that. Let's do some equilibrium stuff with that. Oh, now we got to add to that, Ka times Kb. I don't know of a further step than this. So if we can get to this, again, we're already over halfway done with the class, you guys. We're not going to even get through that reading guide completely that I said on a short day or this not much to do day, because I want to make sure we get through this knowing it instead of rushing through it. One last thing I want to bring up about this. This equation on your equation sheet is written right alongside this equation. Look familiar? Hydroxide times hydronium equals 10 to the negative 14th. There is, underneath that, another equation on your equation sheet. Look familiar? The reason why these 2 equations that I have up here are kind of interchangeable is because of this, and then I could do POH is for the hydroxide. Get all equations that you know. We're going to add one more little equation then that's on this sheet for you to be aware of. That P in front of H, I told you early on, pH stands for power of hydrogen. It's a logarithm scale. Some people, and I think Erin was working on that calculation before, she looked at how the textbook solved it. She's like, I solved it a little bit different, but she got the exact same answer. Because Erin, like I, prefers using pH plus POH equals 14. Small numbers are nice to work with. Power of 10 numbers are sometimes a pain. You type them in wrong, you're wrong. The textbook used hydronium times hydroxide equals 10 to the negative 14th. Well, this right here has big numbers in scientific notation. But just like pH plus POH equals 14 is just from logarithm, there's something called pKa, which is taking the negative log of Ka. That equation is on your equation sheet. So it's just one more thing to think about when we introduce Ka values. That we could give them to you in the 10 to the negative 8th or 10 to the negative 4th value, or we could give you a pKa. Reason why I want to bring this up today is when we start moving into buffer solutions, in the reading guide that we'll get to part of today, buffers will reference the pKa instead of the Ka. There's a reason why. It deals with how good a buffer is at certain pHs, correlates well with the pKa. The pKa value is something that's going to come up with titration math later on as well. So I want you to simply be aware of this. And again, your equation sheet will give you pKa equals negative log of Ka. Just like this one, corresponding to allow that down below to happen. So I want you to be aware of that. I believe WebAssign will reference pKa once because your reading guide is going to reference it. I just didn't know how far we'd get with that reading guide now that I look at the time. So I wanted to bring this up to you as well. This is one more equation. And actually, when I look at the equilibrium section of your calculation sheet, I've now discussed every equation except for one, which is going to be brought up with buffers on this sheet. And then we've covered all the calculation stuff that we need to be aware of. Okay?